Hello, welcome to this second lecture of this week. So, the previous lecture we have discussed about the importance of defining the particle shape and the size. The particle shape, we have shown that for irregularly shaped particle we use a definition called sphericity, and for particle shape, particle size, when we are discussing, we have also discussed that what are the properties that is being influenced by the particle size and why we must know that what is the size of a particle I am going to treat. But friends, it has got the identical problem with our irregularly shaped particles, like what we encountered while defining the shape. Now, say suppose this is the particle, irregularly shaped particle, which commonly we get from the mined products, as I kept on saying repeatedly. Now, what is the size of this particle? We said that for defining the shape of this, we have got some kind of compromise solution or the definition that is called sphericity. Now, as the size, defining size is very important, there are many definitions given. I am just highlighting a few of them, but because of the paucity of time I am not going into the details of all these definitions, but just for your information sake that I am going to show you that what are the popular definitions, and if you have interest to learn more about this, I would request you to go through some of the recent textbooks. Now, sometimes it is called the sphere of same minimum length. That means, what is the minimum length of this particle and what will be the basically the a sphere of that. So, if I imagine that I am having a spherical particle having identical properties with the minimum dimension of this sphere of same weight, like we are always comparing, we are trying to define the size in relation to a known shape, that is where we need only one attribute to define, that is the your diameter or radius. Normally, this is the diameter. So, sphere of same weight, sphere of same volume, sphere of same surface area, sphere passing same sieve aperture, that this one I will elaborate more, and then sphere having same sedimentation rate. Same sedimentation rate means that if I drop this particle into a fluid medium and say suppose its velocity is 1 centimeter per second, and I know the density of this particle is 2500 kg per meter cube. So, what would be the equivalent size of a sphere which has got the same setting velocity, the identical setting velocity, and then sphere of same maximum length, like that. But you see that when there are some proposed definitions, there must be some reasons. So, when we are dealing with this particle, just for example, like when we are trying to design a settling basin, where we want to know that what are the settling velocities of these particles. So, maybe the definition of based on sedimentation rate may be more appropriate. But say suppose the particle size, we want to go for a size separation, a physical size separation, then that definition has got no relevance, your sedimentation based definition. So, we use some other definition. So, friends, if we summarize, we may say that there is no such thing as a universal particle size. lots of definitions exist. Now, to define a single parameter of anything, if you have n number of definitions, that means there is no common agreement between the scientists or between the practicing engineers or practicing people, that okay, this is the definition which is the best and which appropriately define my particle characteristic. So, what is the message here? That be very clear which particle size has been measured in any data you are given. This is a very important issue, and so this is very, very important for practicing engineers. Many times we say that there is the size of the particle, but what size, how it is being measured, how do I define. So, that is what I am trying to suggest, that be very clear which particle size has been measured in any data you are given. Then what I have to do, that where possible measure the particle size that matches your application. That means, suppose the example is here, the particle size was measured by based on the sedimentation velocity, that is the example I have given, and my application is related to packing density. That is, I am trying to find out a place, or maybe I want to design a basically a container where I want to, like we call it bin, that where we want to store, say suppose 10,000 tons of these materials. So, as I said, the packing density will be dictated by the particle size and the particle shape. So, whether what will be the dimension of that bin, that will be that for that I need to know the size, but the size, particle size information whatever I have got, that is basically the definition based on the sedimentation velocity. It does not have any relation to that. So, please ensure that the definition of that size exactly matches your application, otherwise your calculations, your designs may be wrong. If we go to the next thing, that is, what are the units I will use to define the size. It can start with the kilometer, to meter, and even up to angstrom. But this course is related to mineral processing. So, a general curiosity of all of you would be that what is that maximum size in terms of unit and the minimum size we encounter. Actually, when we are dealing with the mined product, when it is directly coming from mines, we may have to start with meter, then your centimeter, millimeter, and we stop here, micrometer. We do not deal with this nano particles and your angstrom sizes particles, but these days some mineral processing engineers, they are researching on the application of some mineral processing techniques to even generate nanoparticles. That is, they are involved in nanotechnology based research. But a common mineral processor, they encounter the particles size ranging from, in terms of unit, that is your meter to micrometer sizes. And most commonly we use the micrometers, because if you remember our discussion on the liberation, because our low grade, we are mining such a low grade ores these days that you have to grind the rock to very fine particle sizes, and you have to define them in terms of micrometers. They are not even in the millimeter sizes many times. That is their liberation, that is dictated by their liberation behavior. When they are very small, that is in this range, the colloid region measured in nanometers. So, how do we measure? Can I use the same identical technique to measure the particle sizes from the meter to angstrom or nanometer sizes? No. So, we use different techniques to measure them. Like I am just giving you an example that for a nanometer sizes particles or angstrom sizes particles, we use electron microscopy, transmission electron microscopy, sometimes dynamic light scattering. So, there are various techniques available. And for coarser particle sizes, we use different techniques which we will discuss very soon. But before we go to this, that how do we measure the particle sizes which are available in assemblage, let me elaborate this point. As I kept on saying that we are not interested in knowing in most of the cases the individual particle characteristics, because we are not dealing individual particles, we have to deal with bulk commodities. So, how the bulk material they behave, that is what is most important characteristics any mineral processor should have to know. Otherwise, you cannot design, you cannot do anything with the subsequent downstream processes. As an example, so what we do? That we try to group them into different discrete ranges. Like this example here, you see that this is an assemblage of relatively some coarser particles down to these particle sizes are more than 1 millimeter, and you find that you have these particles which are even up to 1/16th of a millimeter. So, we have got a assemblage. Now, what will be the characteristics of this? Now, suppose I have got 500 grams of this material, how will they behave? So, that will again be dictated that what are the relative distributions of the each size ranges. So, we cannot define a by single size, that is we cannot say that it is a 1 millimeter particle, because not all the particles are having exactly 1 millimeter size. Some particles may be 0.98 millimeter, some particles may be 1.01 millimeter. So, what do? We try to put them into a range. So, ranges like this half millimeter to 1 millimeter, 1/4 millimeter to half millimeter, 1/8 millimeter to 1/4 millimeter, like that. And then we try to identify some easier technique which is fast, which is cheap, which will give us a segregated information of this assemblage. like that. These particle classes I am showing it as a segregated version, but eventually they were basically mixed. Now, I have grouped them. Now, say suppose out of 500 grams material, I see that 5% of these materials they are greater than 1 millimeter sizes. I am not giving any guarantee that whether you have got any particle more than 1.2 millimeter or 1.3 millimeter, but what I am saying that the 5% of the total population is greater than 1 millimeter. Then this one I am saying that 10% of this population is within a half millimeter to 1 millimeter. Like that we are saying 15% is 1/4 to half millimeter, 30% is 1/8 to 1/4 millimeter, and remaining 40% is 1/8 of a millimeter to 1/16 of a millimeter. Why do we do this? That is a very important question. Now, the very first reason is many times my client for whom I am processing, they say that we are interested only on the size ranges between 1/8 to 1/4 of a millimeter. We are not at all interested in buying these sizes, we are interested in this. So, when I have when I have a mined product which is having this type of your mixed sizes, so I know that whatever I have mined, I can sell to a maximum of 30% of that material to this client, 1/8 of 1/4 millimeter. But then also that information also tells me that if I mine at a rate of 100 tons per hour, I will be able to sell the 30 tons at a rate of 30 tons per hour to the client 1 who will accept 1/8 to 1/4 of a millimeter particles. So, I have to plan beforehand, before setting up that processing plant of a capacity of 100 tons, that what I am going to do with the remaining 70 tons material which are being produced per hour. So, first thing what we have to do, that is whether there is any buyer for these particles, or if you find that there are no buyers, so how do I dispose it of? What do I dump it? Will there be any environmental related problems and all this? What will be the material handling equipment and all this? So, all sorts of information you can have when you have this prior information, that what is the relative distribution, what do we call it, that this is called the particle size distribution. So, as a mineral processing person, mostly we are interested in knowing the particle size distribution, not the individual particle sizes. Sometimes we may be interested in knowing individual sizes, but in most of the cases we want to know the particle size distribution, how they are segregated, how they are distributed in discrete size ranges. That is why we choose certain methods to quickly generate this information out of my mined product. Now, another thing is that particle size and other properties presents an additional problem. They do not have single values like shape, like those particles what I had shown you in the previous slide, that we are not interested in knowing the individual shapes of the particles, because it is extremely difficult. but sometimes we may need to know that whether these particles are in general flaky type or what type of shape it has got or what is their say actually sphericity. Because now say suppose if I go back to this example, now I am producing this material, I am mining and I am processing it sitting in say Kharagpur, and my client wants it to be delivered in a place in Mumbai, which is around 1800 kilometers from this place. So, I have to think of that how do I transport it. So, the mode of transportation will also be dictated by the particle size I already know, but what are the shapes. Suppose we plan to have a pipeline transport through as a slurry. Now, if I have a flaky particle, I have a different problem. If they are spherical particle, I have a different problem. So, my design characteristics will definitely be dictated by their shape distribution. So, that is why we are saying that the particle properties and particle like a particle size and shape, they present an additional problem, they do not have single values. So, that is why we always give emphasis on a particular property in a distributive manner. That is, what is the particle size distribution, what is the particle density distribution, like that. Now, say suppose we have a distribution like this. So, we want to gather more information out of that distributed value. So, what do we do? So, many times we plot like your particle size versus say actually volume versus particle size, or maybe weight percent versus particle size, and we may plot a distribution in the form of basically the histograms. So, from the histogram, if we look at the histograms, we know that these are the suppose the coarsest sizes. So, this is the coarsest particle, it does not have much of, it has got very little percentage in the entire assemblies. Similarly, we can get to know that the finest particles, that the relatively finer particles, their contribution on the overall assemblage is very less. So, what are those particles that is basically controlling the most of the majority of the assemblage at this range, and what is the most common particle size which is being reported. Same data, if we link together, we can have a differential distribution plot, but in mineral processing area we commonly use the cumulative distribution plot. We will have to discuss more on this point. What is the meaning of cumulative distribution? Before that, let me explain a little bit of for your say actually for your say revision of your basic knowledge about elementary knowledge of statistics, that when we have a distribution plot, so we also get to know that what is the mean value, that means what is the weighted average center of gravity, that means what is the mean value, suppose if I have a distribution plot like this. So, the mean value is somewhere here. As the median is the 50% point, that means it is the point where the entire area is equally divided into two parts. And mode, that is the peak of the distribution, that is what I said, that the most common particle which is reporting. So, as the peak of the distribution, that is the most common value. Now, if I have a distribution like this, then all three, this mean, median and mode, they coincide here. But in some cases, you may have this distribution plot like skewed towards left or towards right. So, then your mean, median, modes are different. So, when I look at the shape of the distribution curve, I have some kind of your basic information about the particle size distribution of that assemblage. So, the techniques what we use in mineral processing, that is to determine the size distribution, not the individual sizes. Very rare occasions we are interested to know, mostly in research, in academic research, we try to have the information on the individual sizes. But as we are dealing with bulk commodities, we are more interested in knowing the particle size distribution instead in place of knowing the individual sizes. So, that is called the, so the analyzer, we call it particle size analyzer, in short term it is called PSA. So, again what method we are applying it, because your intrinsic definition of size is different, it differs from the technique to technique. So, what is that size it is measuring to give me the information about the size distribution. So, that is very important. So, what is the method we are using? Obviously, the question will come that why should one consider various methods of particle size analysis? The reason is the material suppliers and users employ many different types of instruments, and you will definitely get different answers when you use different techniques. So, it is important to understand how analysis methods differ in order to know how to compare data. What I am trying to say here? Suppose you give me a data telling me, look, this is the size distribution I am getting, and it tells me that this is the size distribution I am getting, but it is the same sample. Why we are getting the different data? My first question will be to both of you, that how did we ensure that it is the same sample? That means, what is the sampling error? And next question would be, how did you measure the size distribution? If your techniques are different, that means you have measured different sizes. So, definitely they will differ. So, that is why I would suggest you that you should be very clear that what is the definition of the size, or what is that it is measuring, which is telling me that this is the particle size or the particle size distribution. That is what is being measured by that technique. So, that is very important, the analytical methods you have used. So, I will just give you some kind of your summarized information. I cannot elaborate on all this, because if I want to elaborate all this, this itself will become a 30 years course, 30 hours course. So, you see that it is the different techniques also, they have an upper limit of particle size and the bottom limit of particle size restrictions. Like laser diffraction technique, they can go up to millimeter to some kind of your nanometer scale. But if I want to measure 1 nanometer particle size, probably it is not reliable. Dynamic light scattering, light obscuration. So, this summarizes that what is that size range it can deal. So, how does it help you, this summary? Now, if you are interested in knowing the particle size distribution within a range of, say suppose your 1 micron to 100 micron particles, to design your settling basin for dewatering purposes, maybe for water treatment purposes, then the laser diffraction also can do that, 1 micron to 100 micron. Even all these sorts of techniques, they can give you the size distribution about this, but again I am repeating, are they really close to the size what you are looking for while designing a settling basin? That means, why you want to know the size of the particle? Because how do they travel into a fluid medium? So, I would say that use a technique which is based on sedimentation principle, because that closely relate to your process. We will continue this in next module. Thank you very much.